Here we have a particle that's constrained to move along the x-axis, and we have a position function, right? X is a function of t, so we have the position as a function of time over a certain time interval. And we're supposed to find the average position, the displacement, the maximum speed, the turning points, the average acceleration, and the intervals of increasing and decreasing speed. So the first things first, we have a position function, and we want to find the average position over a given interval. We know that to find the average position, the average value of any function is to integrate that function over the integral and divide by the width of the interval. So if we want the average position from the position function, that means that we're going to integrate the position function to find the average position. So here we have the general equation. We're going to integrate the function over the given interval and then divide by the width of the interval to find the average value of that function over that interval. In this case, we have an interval from 0 to 1, so we're going to integrate from 0 to 1. We're dividing by the width of that interval, and then the function is the specific function that we've been given here. So we'll go ahead and evaluate this integral. We'll find a value for it, and we'll use that to find the average value of the position during that time frame. So this value here, 1 minus 0 is 1, and 1 over 1 is just 1. This common factor isn't really contributing anything, but we need to include it for the width of the interval. We perform the integration on this polynomial. We get all these terms, and we're going to evaluate from 1 to 0, so we can plug in 1, and we get all these values. Minus, we plug in 0, and since there's a t in every term, all these values all go to 0. So this is the t equal 1 minus t equals 0. This simplifies to negative 1.83, and that is our average position over that interval. This is a negative cubic function, so it plunges down below the origin between 0 and 1, and so it makes sense that we have a negative average value in that region. The next thing that we are asked to find is the displacement between t equals 0 and t equals 2. Our displacement is delta x. That's what we should think of when we see displacement. And delta x, delta anything, is the final value minus the initial value. In this case, if we want delta x, it's going to be x final minus x initial. Over this interval, that means that we want the final value is going to be our position at t equals 2, and the initial value is going to be our position function evaluated at t equals 0. And so to find these values, we want to find the position at t equals 2. We can find that by evaluating this function. After evaluating these two, the function of these 2 points, we can plug in 5 minus a negative 7 makes this a positive 12 meters. Displacement is a distance, and we're measuring our distance in meters, so our displacement will have units of 12 meters there. The next thing we're asked to find is the particle's maximum speed on the interval. The maximum speed is going to be where we have where we maximize the velocity function. We find the maximum velocity. So the first thing that we need to do is to find the velocity function. So we know that the velocity is the derivative of position. We have a position function here, and so we'll need to differentiate that position function. So we take our derivative and we apply it to the original function that we have. So, we can differentiate each term separately. We know how to differentiate polynomials, and that gives us our velocity as a function of time. This gives us our velocity everywhere on this entire interval. If we want the maximum speed, where the speed is the magnitude of the velocity, that basically means we want to maximize the velocity, and we're looking for the largest positive or largest negative velocities. But to maximize the velocity, what we do is to maximize any function would be to take the derivative of that function and set it equal to 0. This is what we call optimization. And it's what you've done in calculus class to find the maxes and mins of a function. So I can differentiate my velocity function. And I set that equal to 0. And I have solved for the value of t for which my derivative equals 0. That's where I have my maximum or minimum values. If I'm looking on a fixed interval, I also need to check the endpoints of that interval to see whether those are my maximum values, and I'm just not seeing them because they're not true maxes or mins where the velocity equals 0, but they're the maximum, or the local maxes or mins because of the cutoff of the interval. So I'm going to go ahead and check my velocity at 0 and at 3 at the two endpoints, and then also at 1/3, and see which one of these are maxes and mins. Here I have evaluated my velocity function at the two endpoints and at the optimization location, the value of t for which I have a local max or min, and I see that my maximum speed is going to be here. The negative sign means that I'm moving to the left, but this is the largest value. The speed is the absolute value, the magnitude of the velocity. So this is going to be my maximum speed that occurs at t equal 3. The next thing that I want to find are the turning points. The turning points are where the particle turns around, changes direction. So in this situation, what I want to do is figure out where the particle is not moving left or right, but rather where the particle is motionless. So my turning points are going to be where velocity equals 0. If I can figure out where my velocity equals 0, I figure out where my particle is at rest, and then I can figure out if it's at rest at all other places where v is not equal to 0, then I can figure out whether I'm moving to the right or to the left. But these places where I'm at rest are where I pause to change direction, and those are my turning points. So to use this, I want to hold on to my velocity function that I already calculated, and I'm going to use that. So here I have my velocity function, and I want to find my turning points. Again, my turning points are where my velocity equals 0, so I'm instantaneously at rest as I stop moving one direction and I start moving another direction. This here is a quadratic equation where I have a t² term, a t term, and a constant, and the whole thing equals 0. So to solve a quadratic like this, I'll use the quadratic formula, which is something that you should have memorized. I get two solutions to a problem where I have a t². In this case, one of those solutions is in my interval, the other one is not, and so I can throw that one out, and I can say that my turning point here is at 1.67 seconds is when the particle changes direction during this interval. My next task here is to find the average acceleration on a given interval. The average acceleration is defined as the change in velocity over the change in time. That's what an acceleration, average acceleration is defined as, how much the rate of change of the velocity. In this case, this is going to be the delta v means v final minus v initial, and delta t is going to be t final minus t initial. If I'm interested about this interval from 1 second to 2 seconds, that means that I'm going to have v final is going to be the velocity when t equals 2, v initial is going to be the velocity when t equals 1, and then 2 and 1 are my times. I can find these values by evaluating my velocity function directly, and I'm going to do that right now. Now I can plug these values in. And that gives me negative 14 over 1 is just negative 14 meters per second squared, because this is an acceleration, and it's measured in meters per second over seconds is meters per second squared, are my units there. And then finally, I'm asked about the intervals of increasing and decreasing speed. And so if I'm looking for increasing and decreasing speed, whether the particle is speeding up or slowing down, that's going to be dependent on whether the acceleration and the velocity are in the same direction, they're both positive and they're both negative, or whether they are in opposing directions. I already have my turning point here, so I can figure out the direction of the velocity. I also need to compare the direction of the velocity to the acceleration, so I'm going to need an acceleration function. I know that the acceleration is the derivative of velocity, so I can find the acceleration function by differentiating my velocity function. Here I have my acceleration as a function of time. If I want to know whether the acceleration is positive or negative, so I can compare it to the velocity, whether it's positive or negative, the way for me to narrow that down is to figure out where the acceleration is neither positive nor negative, but rather to see where the acceleration equals 0. And from there I can find when t is 1/3 of a second, or 0.333 seconds is when my acceleration equals 0. So what I'm going to do now is look at a number line. This is 0 and this is 3, because that is the overall interval that I'm interested in. I know that something happens at 1/3 of a second. That's when my acceleration is changing sign. I know that something happens at 1.67 seconds. That's where my velocity changes sign, potentially. So looking at my acceleration here, I can plug in a value less than 1/3. I can plug in like t equals 0, for example. If I plug in 0, this term goes away. That's going to be greater than 0, so my acceleration is positive here. If I plug in a value on the other side of 1/3, if I plug in acceleration of 1, for example, this is less than 0, and so my acceleration is negative everywhere to the left, to everywhere above, everywhere past t equals 1/3. I can look at my position function as well, my velocity function as well. If I evaluate this function at some value less than t equals 1.6 seconds, so if I evaluate at t equals 0, I get 0 plus 0 plus 10, that's a positive value. I could evaluate at another value over here, but I should get the same amount. If I plug in like t equals 1, I get -6 plus 4 plus 10 is going to be 8, which is still positive, so I still have positive velocity there. And then if I pick a value past here, so if I pick, for example, t equals 2, I get a value that's negative, that's less than 10, or less than 0. And if I picked any other value over here, I should get the same behavior. So what I am noticing here is that in this interval here, this is speeding up. And this is also speeding up because my velocity and my acceleration have the same sign. Here I'm going faster and faster to the right. Here I'm going faster and faster to the left because of the sign of the sign, SIGN sign of the velocity and acceleration, but I can tell that these are speeding up. Then I can look in this region here, and I can see that we're slowing down because my velocity and my acceleration have opposing signs, and so I'm slowing down in that region. If I want to be very precise in my writing, I can say that I'm speeding up on this interval that starts from 0 and ends at 1/3 or 0.333. So I'm starting it from 0, I'm ending at 1/3. The normal parentheses here mean that I'm excluding these 2 points because here I'm not speeding up or slowing down, but I have a 0 acceleration at that point, so that's why I'm not including that exact value in my interval, but just up to that value. This means the union, so I'm saying this interval plus this interval as well. This interval here starts at 1.67 and runs to 3, so it's referring to that interval there. Again, exclusive, I'm not including the endpoints with the regular parentheses. I'm slowing down in this region here from 1/3 to 1 2/3, and so I'm starting at 1/3, I'm ending at 1 2/3 seconds. So those are my intervals of increasing and decreasing speed.